Hello class. So as the course is ended, so we will do one thing. We will do recap of all the important questions so far we have discussed, so that it will be easy for you for the exam. Okay. So we will start from some easy questions. Okay. So the first question is, find the function f of x for which x f of x equal to minus I by h cross a square p of x f of x, and you have to find the f of x. So the eigenvalue equation is given: x times f of x equal to minus I over h cross a square p of x f of. Okay, so as you can see clearly, there are f of x on both the sides. That means it's a eigenvalue equation, and you can identify easily that there are two operators here, left hand side and right hand side. And if we are dealing in the coordinate space, then this momentum operator, it will have some form in terms of the coordinate basis. So in coordinate space, px will have the form minus I by x cross okay not I by x cross, it's I minus I h cross del over del x. Okay, now if we substitute this in the above equation, what we will have minus I over h cross a square we already had, then minus I h cross del over del x f of x, right? So further simplifying this, minus I it will give us minus 1, and h cross cancel, so minus a square del over del x f of x. It will give us x f of x, right? Now you might be thinking which solution will give us the correct answer. So there is a hint here, like there is a square in this left hand side. So you see the solutions with a square is only c. Let's try this c. So c solution. So let's assume f of x equal to k e to the power minus x square over 2 square. Okay, now doing del over del x f of x, this will give us k and derivative of this one, so this will give us minus 2x over 2a square e to the power minus x square or 2a square. So 2 cancels on both the sides. Okay, not both the sides, numerator and denominator. And this k along with this function, it gives what? It gives f of x, right? Then what remains? Minus x over a square remains, right? Now we didn't write this term here, so let's write this minus a square del over del x f of x equal to x f of x. So this will give us minus a square, and this term we already got from here, minus x over a square f of x equal to x f of x. Okay, now this minus minus cancels and a square cancels. So you have ax f of x on left hand side and ax f of x on right hand side also. So this equation is satisfied. So the correct answer should be C. Right. Now moving on to the next question. Okay. So a particle which is initially at initial time t equal to 0, it was in ground state of infinite one-dimensional potential box. So the question is given like there is an infinite potential world which lengths are x equal to 0 to x equal to a. And this potential world is to infinity. Okay. Now there is a perturbation added to this system. This perturbation is expressed as x square e to the power minus t over tau. Okay. Now we have to calculate the first order probability finding the particle in first excited state for t equal to t greater than or equal to 0. So initially what was the at t equal to 0 the particle was in the ground state. Okay. Now at t greater than or equal to 0 it's in first excited state. So at t equal to 0 n equal to 0 and t greater than 0 this is n equal to 1. Okay. So what you have to calculate? We have to calculate the probability of this kind of transition. Okay. So any suggestions how to proceed? Okay, so let's do this. Okay, so initial state was n equal to 0 state and the excited state is n equal to 1 state. So applying the following golden rule, the probability of transition from initial state to final state, let's write this for EFI is a function of t. This will be 1 over x square mod of 0 to infinity e to the power minus I omega fi t and the transition moment integral e of t I 1. Okay, it's okay, we can write it as initial, this is final. So it's not 1 2, it's initial and final. Okay, so So initially okay, so this is a 1D potential. Maybe n does not start from 0, starts from 1. Okay, so in that case n equal to 1 to n equal to 2. Right. So we know the wave function for 1D potential. This will be root over 2 over L sine n pi x over L. Okay. Now our initial state has n equal to 1 and final state has n equal to 2. So let's evaluate this transition moment integral first. This psi 2 v of t psi 1. So this will give us integration. So this psi 2 will have some constant root over of 2 over L, and other wave function it will have also that same constant. So what we can do, we can take out that common constant outside. So we will have root 2 over L outside. Then what remains? Then all remaining thing is sine pi x over, okay, the length was A, so this is A, not L. Okay, then b of x is x square e to the power minus t over tau. Then okay, this is final, so it's 2 pi x, and this is sine pi x over A dx. Okay, and limit will go from 0 to A. The other limit means if it goes from minus infinity to infinity, then from minus infinity to 0 there is no potential, so it will be 0, and from A to infinity there is also no potential, it will be 0. So if I write from 0 to infinity or 0 to A, it's same thing. Okay, now you see this function e to the power minus t over tau, it does not depend on the it does not affect the integral, so we can take it out simply. Okay, this is whole square, so this integral will give us 2 over L to the power minus t over tau, then integration of x square sine pi x over A and sine 2 pi x over A dx, limit from 0 to A. Okay. Now we have to evaluate this integral by using integration by part. But you see there are 3 functions now. So what we have to do, we have to convert the 2 functions to a single functional form. Okay, so you see this is in the form of sine A times sine B form. Okay, so we know from the identity sine 2 sine A into sine B, this we can write as cos A minus B minus cos A plus B. Right, now we can rewrite this sine function as Okay, so let me take this as 2 over L e to the power minus t over tau, and this integration 0 to a x square. Okay, as there is no 2, we have to divide by 2, so I am taking this 2 outside. Then it's cos a minus, okay, a minus b. Let's take this is a, this is b. Then in that case, this will give us pi x over a minus cos 3 pi x over a. Right. Now, if you evaluate this by using integration by parts, so this is integration of u times v. So if you evaluate this, then you will get f. Okay, I am not doing all the steps. If you evaluate this, you will get final answer to be minus 16a square or 9 pi square into the power minus t over tau. Okay, so you got the transition moment integral form. Now it's pretty simple. You have to calculate the probability pfi of t. This will be 1 over x square, then mod of e to the okay, integration 0 to infinity e to the power minus I omega fi e to the power minus t over tau dt mod square. Okay, now okay, I have substituted the value here, so let me write the constant also, 16a square over 9 pi square outside. Okay, so this is the there is one more integration we need to solve now. So we see that there are t common in both the exponential. So what we can do, let me write down the constant first, 16a square over 9 pi square x square. So what I can do, I can take common t, so it is omega fi minus 1 over tau times t dt mod square. Okay, now this integration is with respect to t, so it's pretty straightforward. It's easy to do now. 16a square over 9 pi square x square. Now this will give us for I omega fi minus 1 over tau t I omega fi 1 over tau 0 to infinity mod square. Okay, now as you know, e to the power something, its radius e to the power I z, it's a circle in complex plane, right, with radius 1. Okay, so if any radius is multiplied with it, so it will be scaled by that vector r radius. Okay, so only e to the power iz factor is given, that means its radius is 1. And taking mode of this kind of function is doing what? Taking mode of this kind of function means we are calculating the radius. So e to the power I z mod, it will give us 1. Okay. So if we do the mod, then what will remain? 16 square over 9 pi square square over I by 5 minus 1 over tau mod square. This will only remain. And now you see this is a plus ib form. So mod of this kind of function will give us a square plus b square. So further simplifying this will give us 16a square by 9 pi square a square square. This will give us 1 over tau square plus omega fi square. So this is the probability of transition. Okay. Okay, then moving on to the next question. In the presence of electromagnetic field, the Hamiltonian is 0 equal to p square by 2m plus dx will change to what? Okay. So in the presence of electromagnetic field, what changes? The momentum changes. So this momentum changes to p plus momentum changes to p plus p prime. P prime comes from on the contribution of this electromagnetic field. Okay. So this P in the presence of electromagnetic field will be having the O minus Q A. Okay, so this will take the form P minus Q A. So this P will change to P minus Q A. Okay, so in that case D will be the right answer. Okay. Then moving on to the next question. Okay, which of the following is the correct expression for the relation between Einstein coefficient A and B? Okay, so the correct answer will be A. This is the correct relation between A and B. This ratio A over B, this will give us 8 pi mu q h over c q. Okay, so the correct answer is A. Okay, then moving on to the next question. Okay, If the frequency of emitted photon is 10 Hz, then the ratio of Einstein coefficient A over B will be how much? So just now I gave you the formula. So it's pretty straightforward. You know the frequency and you know all the constant values. So you have to put all the values, then find out the answer. Okay. Okay. So the ratio of Einstein coefficient A over B, it will give us 8 pi 8 pi nu cube h over c cube. 8 pi h nu cube over c cube. Okay. So nu is given to 10 Hz or 10 second inverse. Okay. Now you can put all the values. 8 times pi times 10 cube times what is the value of Planck's constant? It's 6.6 to 10 to the minus 34 joule second, and value of C, this is 3 into 10 to the power 8 cube. So if you put this in calculator, it will give okay 6.6 is cube this will give us 61177 times 10 to the power minus 50. Okay, so D will be the right hand side. Okay, and then moving on to the next question. Examine how A and B coefficients depend on length for a one-dimensional square well of length. Okay. Now, well, for the transition n to n minus 1. So there is a one-dimensional well of length L. Okay, and there is a transition from n equal to n state to n minus 1 state. Okay, then how does the A and B coefficient will depend on this length? Okay. Now, the A and B coefficients, this will be proportional to the transition moment integral. Okay. So this will be proportional to the transition moment integral psi f mu times c psi f. Okay. Actually, these will be proportional to their mod square. Now, if you get any of the constants first, then from the relation by A to B, A by B, 8 by h over c cube. In this relation we can get A. So first we can calculate B. So B can be written as pi over 6 epsilon naught x cross square times the transition moment integral n minus 1 Okay. Now if I evaluate B, then from B I can get A also from this relation. Okay. No, so now I have to first evaluate this transition moment integral. So for one-dimensional potential, you know the wave equation, wave function psi n to be 2 over L sin n pi x over L. Okay. So similarly for psi n minus 1, this will become 2 over L sin n minus 1 pi x over L. Right. So what we have to do, we have to first evaluate the transition moment integral. 9 minus 1 so this I can write as 0 to L psi n minus 1 star then mu times epsilon. Okay, so mu is dipole moment, right? So let's assume this is a dipole and it's in a electric field. So in that case, what will be the dipole moment? It will be, say, charge. Let's say this is electron, so it will be minus e. That charge times radius, right? So the dipole moment is charge times radius. So if I assume this to be along the x-axis, and let's say the distance is x between them, so in that case it will become e minus ex. Okay. And this electric field, this is along x-axis. So in that case, mu times e cap will give us minus ex. Okay, in that case it will become minus ex sin dx. Okay, so you will substitute this wave function, then you will get minus e 2 over L. These are constants. I took this outside. What will remain? X times sine n minus 1 pi x over L times sine n pi x over L dx. Now you apply the same identity sin A into sin B, then you will get cos A minus B minus cos A plus B form. Now if I directly put the identity directly here, what I'll get 1 over 2 I'll take outside, then x times cos pi x over L minus cos 2 minus 1 pi x over L. Okay. 12 do 2 cancels. Okay. Now if you solve this, I'm not going to do all that detailed calculation. So if you solve this, so you will get this to be 2e L square over L over pi square minus 1 over 2 minus 1 pi or something. So you see this will cancel. So this transition moment integral, this will be proportional to L. So our formula for B was, it was directly proportional to the transition moment integral square. So in that case, B will be proportional to L square. So we don't need the exact form, we need the relation. So B will be proportional to L square, and from this we can apply this formula, A over B equal to 8 pi h mu cube over c cube. So this relation we can apply. So you see all these values are constant. So what is the variable now? Nu cube. So nu is the frequency of photon. So in this case of one dimensional potential, the energy of nth state we can write as n square h square over 8 ml square, right? So if one transition is happening from n state to n minus 1 state, state to n minus 1 state, so what will happen? One photon will be released. Okay, so in that case the energy difference between these two states should be equal to this energy release, right? So h nu should be equal to En minus 1, right? So this will be equal to n square h square over 8 ml square minus n minus 1 square h square 8 ml square. Okay, now all other things are same. I can take common. So this will give me n square minus n minus 1 whole square times h square over 8 ml. So this will give me mu equal to n square minus n minus 1 square 8 over h over 8 ml square. So what I need the dependence of L on the frequency. So what is the dependence? Nu is proportional to L to the power minus 2. Okay, so nu is proportional to L to the power minus 2 and B is proportional to L square. So in this case, what will happen? A will be equal to B times, okay, A will be proportional to B times nu cube. Okay, so B is proportional to L square and nu is proportional to L to the minus 2, so it's cube. Okay, so this will give me L square times L to the minus 6, or A will be proportional to L to the minus 4. Okay, so A will be proportional to L to the minus 4 and B will be proportional to L square. So we have A proportional to L to the minus 4 and B proportional to L square. So this is the correct answer. Okay. Moving on to the next question. Okay. An ensemble of 10 to the power 5 identical atoms in an excited state with Einstein coefficient A equal to 2 into 10 to the power 7 second inverse. Then calculate the spontaneous emission rate. So, you know the rate of transition minus d n over dt. This is equal to, this will be proportional to the number of particles and this will be directly proportional to the Einstein coefficient A. Okay. So this rate can write as A times n. Okay. So in that case A is given and n is also given. Okay. So what we can do, we will multiply those two. 2 times 10 to the 7 to the 5. So this will give us 2 times 10 to the 12. Okay, so this is the spontaneous emission rate. Okay. Spontaneous emission rate. It is straightforward. Okay. Just give me 5 minutes. Okay, moving on to the next question. A certain radioactive isotope undergoes spontaneous decay with half-life 10 days. Then calculate the rate of spontaneous emission for this isotope in decays per second. Okay. Just now we told the decay rate dN over dt. This will be equal to n times A. Okay. Now if you solve this, minus dN, it will be equal to NA times dt, or this dN over n will be equal to minus A dt. So if you integrate both the sides, so it will give you ln of n minus A plus some constant, or this n of t will be equal to n of 0 e to the power minus at, where this n of 0 is the proportionality constant. Okay. Now what is given? The half-life is given, so t half is given 10 days. Okay. So what will happen at this time? The number of particles in the excited state compared to the ground state will be half. So that means n of t, n of 0, this will be half. Okay. Or this will be equal to e to the power minus a times t half. Okay. Now what we have to calculate? We have to calculate the spontaneous emission rate. That means we need to calculate this Einstein coefficient A. Okay, so if I do one thing, I take a logarithm on both the sides, ln of e to the power minus a t half. This will give me ln half, or minus a t half is ln of half. If I take minus sign to right hand side, then this will give me a t half equal to ln of 2. Right. Then the value of Einstein constant A will be nothing but ln of 2 over t half. Right. Now this ln of 2 divided by t half is 10 days. Now I have to convert it into seconds. So 10 days to times 24 hours times 60 minutes times 60 seconds. Well, I have to calculate this Einstein coefficient A. Right. Now if you put this in your calculator, this will give you 8.022 times 10 to the minus 7 seconds. So this is the spontaneous emission rate. Okay, so this is not 18, this is 8. Okay, then we'll move move on to the next question. Which term in the transition probability determine the safe? So the correct answer will be B. So due to this factor, we'll have the form like Gaussian distribution, right? This function is another form of this Gaussian distribution. So this term will give us the shape of the probability distribution, right? So the answer will be B. Okay, then moving on to the next question. Okay. So the relation between Gaussian and Lorentzian line width. Okay, which one is the correct answer? Okay. The Lorentzian distribution comes from intrinsic parameters. Okay. And the Gaussian distribution, it is influenced by external variables. So its shape will be slightly flatter than the Lorentzian distribution. Okay, so in that case you can clearly visualize this line width will be more for Gaussian distribution compared to the Lorentzian distribution. So the correct answer will be C. Okay, so moving on to the next question. At time t equal to tau, tau is natural lifetime. Which of the following is true for spontaneous emission? Okay, so from the name you can guess it. Natural lifetime. That natural means this factor E. Means, at this time the number of particles in excited state reduced by a factor of E compared to the ground state particle. Okay, so this n of t is nothing but n of 0 times e to the power minus a t. Okay, now at t equal to tau time, what happens? This tau is nothing but 1 over a. Okay, so what happens at this tau equal to a, sorry, t equal to tau time. So if I put tau equal to 1 over a, so what will happen? E to the minus 1. So this will give me n of 0 time divided by e. So what is happening? At this time, the number of particles in excited state are decaying by a factor of 1 over e. So the correct answer is B. Okay. So moving on to the next question. So the microwaves spectrum of potassium iodide consists of a series of lines whose spacing are almost constant at 3634 megahertz. Then calculate the bond length for this potassium iodide. Okay. So what is given? Series of lines whose spacing are almost constant. That means the spacing are constant. So these are the series of lines. The spacing are constant. That means you know this spacing is nothing but 2b. So 2b is given. What you have to calculate? The bond length. Potassium iodide. You have to calculate the bond length R0. Okay. So now what I can get from this kind of system. So if it is a diatomic molecule, it will have rotational energy, right? So it will have rotational spectrum. So if we consider this to be a rigid rotor, then it will have moment of inertia. That's denoted by IE. Okay. So we know this rotational constant B we call it as rotational constant. We can write this rotational constant as h over 8 pi square IE. Okay, where IE is the moment of inertia. Okay, now if I rewrite this equation in terms of IE, I will get h over 8 pi square b. Let me arrange this. It will be h over 4 pi square 2b. I wrote this 2b because 2b is given in the question. Okay, this is 2b. Okay, from this I got the moment of inertia. So there is another formula for moment of inertia. So I can write IE as mu times RE square or R naught square. Okay. So we got IE in terms of rotational constant. Now we have IE in terms of bond length and reduced mass. So we can substitute, equate these two equations, then we will have mu R naught square will be equal to h over 4 pi square 2, right? Then R naught square will be h over 4 pi square mu times 2b. Okay, or R naught will be equal to root over of h over 4 pi square mu times 2b. Okay, so 2b we know, and this is nothing but 3634 megahertz or 3634 times 10 to the power 6 hertz or second. Okay, this value we have. So we don't know the reduced mass, but we know the system potassium iodide. We can calculate the reduced mass. Reduced mass is m1 times m2 divided by m1 plus m2. Okay, let me write down here mass of potassium times mass of iodine divided by mass of potassium plus mass of iodine. So this will give me 39 times 127 divided by 39 times 127. So this will be in terms of atomic mass unit. So to convert this atomic mass unit to kg, we have to multiply some factors. So if I convert it to kg, I will get 4.9 times 10 to the power minus 26 kg. Some new value we got. To b we have already. H is Planck's constant, and then you have all the values. So if you put all the values in the above equation, the R naught value you will get is 305.560. Times 10 to the power minus 8 meter, or 3.05 times 10 to the power minus 10 meter, or 3.05 Armstrong. Okay, so what was given? The spacing was given, that means 2b was given. So from that we calculated the moment of inertia for this particle, and we know another formula for moment of inertia in terms of reduced mass and bond length. Then we equated these two equations, and from that we got the value of R naught in terms of reduced mass and 2b. And this reduced mass we can calculate from this formula. Now putting all the values, we got the bond length to be 3.05 Armstrong. Okay. Now moving on to the next question. Assuming the rotation of diatomic molecule in J equal to 10th state may be approximated by classical mechanics, or you can call it as a rigid rotor. Then calculate how many revolutions per second sodium chloride makes in J equal to 10 rotational state. The rotational constant for sodium chloride is this much. Okay. So what is given? Rotational constant value is given. That means B is given 6500 megahertz, or 6.5 times 10 to the power 9 second inverse. Okay, so B is given. Now what do you have to calculate? You have to calculate the revolutions per second for this molecule. Okay, let's draw this sodium chloride. So you can approximate as and this as rigid rotor in classical mechanics. So in that case, it will have moment of inertia, that's IE, and it will have some angular frequency omega, with which it will be rotating. So in terms of this moment of inertia and angular frequency, we can write the energy of this system as half IE omega square. Okay, Now from this rotational spectroscopy we know the energy in the jet state as hbj times j plus 1. Okay, so from quantum mechanical formula we know the energy of the jet state as hb times j into j plus 1, and from classical mechanics we know the energy formula to be half ie omega square. So what we can do now, we can equate these two equations. So what we will get, half ie omega square equal to hb j times j plus 1. Okay, now what we have to calculate, the revolutions per second. So that means we have to evaluate omega first. So let me write this equation in terms of omega. This omega square will be 2hb times j into j plus 1 divided by I. Okay, or you know the relation between moment of inertia and rotational constant. So B is equal to h over 8 pi square IE, or you can write IE as h over 8 pi square B. Okay, now what I can do, I can substitute this IE in this equation. So this will give me 2hb j into j plus 1 times 8 pi square b over h. So h is cancelled. I'll have 16 pi square b square times j into j plus 1. This is the value of omega square. Then omega will be 4 pi b times root over of j into j plus 1. Okay, so this is the angular frequency. Okay, so j is given to be 10. Right, now b is also given in this question. B is given 6.5 into 10 to the power 9 per second. So this will be 4 pi times, this value is 6.5 times 10 to 11. So if you solve this, you will get a value around 8.57 times 10 to the power 11. So this is angular frequency, right? So its unit will be radian per second. Okay, so what is being asked in the question? We need to calculate the number of revolutions per second. Okay, so one revolution is 2 pi radians. Okay, so to calculate number of revolution, what we have to do, we have to divide by 2 pi. So 8.57 times 10 to the power 11 divided by 2 pi, or you can where's my break? So this will give us 1.36 times 10 to the power 11 rotations per second. Okay, so in the question, B V was given, and we need to calculate the number of revolutions per second. So for that we need to calculate omega first. So as we have assumed this system to be classical, so energy can take the form half IE omega square, and from rotational spectroscopy we can have energy of this form HB J times J plus 1. So after equating these two forms of energy, we got the formula in terms of omega. Now putting all the values, we got the rotation per second to be 1.36 times 10 to the power 11 rotation per second. Okay. Now moving on to the next question. Okay. The far infrared spectrum for potassium chloride has an intense line at 273 centimeter inverse. Then calculate the force constant and period of vibration for potassium chloride. Okay. So 1 second. Okay. Okay, for this potassium chloride system, so what is given, intense line 278 centimeter inverse is given. Okay, so it's in terms of wave number, so this new bar is given to be 278 centimeter inverse. Okay, now if we consider this system to be a rigid rotor, then it will have energy half IE omega square, right? Now it has some vibrational energy, so we can approximate it to be nearly equal to simple harmonic motion. So in that case it will have energy of half k RE square. Okay, so we have two kind of energies. Now what we have to do, we have to equate them. So this will give us half IE omega square equal to half k RE square. So this k is nothing but force constant. Okay, now we can write this equation in terms of k, as k will be IE omega square over RE square. Okay, now we know the moment of inertia. We can write it as in terms of this bond length R E square. Okay, let me write it properly. So this moment of inertia we can write in terms of this reduced mass and bond length R square is this mu RE square. So now substituting this IE in this equation, it will give us mu RE square omega square over RE square So this will give us the value of k in terms of mu and omega square. Okay, now omega is the angular frequency. So omega is angular frequency. We can write as 2 pi mu. So if I want to write in terms of wave number, so what I have to do, we can simply multiply c, then in terms of wave number I can write like this. Okay, so omega will be 2 pi c times nu bar. Now substituting this in the above equation, we will get k equal to mu times 2 pi c nu bar whole square. Okay, now nu bar is given 278 centimeter inverse, and mu you have to calculate. What is the system? This is potassium chloride. Okay, so mu we can write 39 times 35, 39 plus 35 times some constant. This will give you in terms of kg, so this value will be 3 times 10 to the power minus 26 kg. Now putting all these values will give us the value of k to be 83.92 Newton per meter. Okay, so in our system of potassium chloride, there is an intense line at 278 centimeter inverse. Okay, and the system is also vibrating. So in that case, we can assume this vibration to be simple harmonic. So we can take its energy to be half r square, and from a rotational motion it will have energy half ie omega square. Equating these two energies and solving, we will get the force constant k in terms of reduced mass and angular frequency. So further solving this will give us the value of force constant to be 83.92 Newton per meter. Okay, now moving on to the next question. Okay, so the relation so the selection rule for the rotational spectroscopy dictates that the change in quantum number J must be equal to which one? Okay, so according to selection rule, this change in total angular momentum should be equal to plus or minus 1. So what does this mean? In this rotational spectrum, it can jump from J to J plus 1 or J to J minus 1. Okay, so that's the meaning of this selection rule. So it can make a transition with an amount where the change in total angular momentum will be of 1 unit. So in that case, the right answer will be B and D. Okay, so moving on to the next question. Calculate the ratio N1 over N0 for molecules in J equal to 1 and J equal to 0 rotational levels for carbon monoxide at 25 degrees Celsius. Then assume the this system to be a rigid rotor with BE power of this value. Okay, so the system is carbon monoxide, and so it will have some bond length R0, and as it is having rotational motion, it will have some rotational constant B. So if I write BE, so it will be in terms of hertz, or if I write BE bar, then it will be in terms of centimeter inverse. Okay, so in that case, let me write down the energy of jth state, BE J times J plus 1. Okay, in terms of this wave number, so let me write E bar B bar. Okay, so there is a transition from J equal to, there will be some transition from J equal to 0 to J equal to 1 state, let's say. So in that case, what will be the change in energy? Let's not write it as energy, let's denote it as Fj. Okay, so in that case, what will be the change in this F or energy? Okay, so this will be Fj plus 1 minus Fj. Okay, so this will be giving Be tilde Fj plus 1 times J plus 2 minus Be tilde J into J plus 1. So this will give me 2 times Be J plus 1. Okay, so this is the change in energy. Okay, so the transition is happening from J equal to 0 state to J equal to 1 state. So J is equal to 0 here and J plus 1 is 1. Okay, so J is 0. Now what will be the energy? Delta E, this will be 2 Be tilde. Okay, now the number of particles in excited state or J equal to 1 state divided by the number of particles in the ground state or J equal to 0 state, this will be given by this Maxwell distribution e to the power minus delta E over kT. Okay, where K is Boltzmann constant. Boltzmann distribution. Okay, so delta E, we have the form in kT at this temperature is given to this one. Okay, so Be value is given, so if we put all the value here, so we will get e to the power minus 2 times Be is 1.932 divided by kT is 207.2. So this will give us 0.9815. Okay, now you know for J, for any J value there will be 2J plus 1 degenerate states. Okay, now if J equal to 0, there will be 1 state. If J equal to 1, then there will be 3 degenerate states. Okay, so in that case there will be 3 states with exactly same energy in the J equal to 1 state. So in that case what we can do, this N1 over N0 we can write 3 times e to the power minus delta E over kT, or you can write it as 2J plus 1 times e to the power minus delta E over kT. This is the general form, or this will become 3 times 0.9815. Okay, this N0 over N1, so this will become 2.945. Okay, so N1 over N0. Okay, so what does this mean? So N1 will be 2.945 times N0. So in this J equal to 1 state, there are almost 3 times more particles than the ground state. Okay, this equation means that. Okay, so what was given? At this 25 degrees Celsius temperature, this carbon monoxide will have some rotational motion. Okay, and this rotational constant BE bar are given. Then we need to calculate N1 over N0. Okay, so we calculated the energy difference between these two states. So according to Boltzmann distribution, this ratio will be equal to e to the minus delta E over kT. Now delta E we calculated from here, and kT value is already given. So if we put this, we will get the answer about 0.9815. Again, for J equal to not 0, there will be 2J plus 1 degenerate states. Okay, degenerate state means the energy of each state will be equal. So for J equal to 1 state, there are 3 degenerate states. So in that case, this N1 over N0 form will change to 3 times as e to the power minus delta E over kT. Or finally, we will get N1 over N0 to be 2.945. Okay. So moving on to the next question. Okay. So calculate the ratio N1 over N0 for molecules in N equal to 1 and N equal to 0 vibrational states for carbon monoxide. Okay, at 25 degrees Celsius. Assume harmonic oscillation with frequency or wave number this much. Okay, so in previous question the motion was rotational motion, and in this question the motion is vibrational motion. So for vibrational motion we can assume the motion to be nearly equal or approximate to be simple harmonic oscillation. So in that case, for simple harmonic oscillation the energy will be, or this is given in terms of wave number, so let me write E bar. This will be equal to n plus half V bar. Okay, so if there will be a transition, then the energy difference between these two states, let's write it to be delta E. This will be equal to nu E bar times 1 plus half minus mu E bar 0 plus half. Okay, so n equal to 1 here, and this is n equal to 0. Okay, so if you solve this, you will get mu E bar. Okay, so this change in energy will be equal to mu E bar. Okay, now we need to calculate n1 over n naught. Okay, so applying Boltzmann distribution, we will get n1 over n naught to be e to the power minus delta E bar for kT. So for this temperature 25 degrees Celsius, kT value is given, and E value, delta E value we calculate, which will be equal to this nu E bar. So putting all this value, we will get this to be e to the power minus 2169.8 over kT is 207.2. Okay, now if you solve this, you will get this value to be 2.83 times 10 to the power minus 5. So if you compare this same kind of situation compared to the previous question, where the motion was rotational motion and here the motion is vibrational motion. So there at this temperature 25 degrees Celsius, most of the particles were in excited state, and here most of the particles are in ground state. So the energy produced by this vibrational motion is not enough to excite a particle. Okay, at least compared to the rotational motion. Okay, then moving on to the next question. Okay, two adjacent lines in the rotational absorption spectrum of this NH molecule are at 98 and 130 centimeter inverse. Then calculate the equilibrium bond length for this molecule NH and the rotational quantum numbers of the lower states of the two transitions. So what is given? Two adjacent lines are given. One is 98.036 and another one is 130.714 centimeter inverse. Okay, so what will be the spacing between these two lines? This will be 2b. Okay, or in this case let's write this to be 2b bar, as it is in terms of centimeter inverse. So 2b bar will be equal to 130.714 minus 98.036. This will be equal to 32.678 centimeters inverse. Okay. So 2b bar is this much. Okay. Now what do we have to calculate? The equilibrium bond length. Okay, now the equilibrium bond length is given. No, it's not given. Okay, so we need to calculate the equilibrium bond length and the rotational quantum numbers of lower states. Okay, so each line will be from some transition, right? Let's say J from J state to J prime double prime state to J double prime plus 1 state. Okay, so each line will be coming from this kind of transition, right? Now, so if you okay, so in previous questions we calculated the energy difference between these two lines. So this delta F, this will be F J double prime minus F J double prime plus 1 minus F J double prime. So this will be of the form 2B bar and J double prime plus 1, where this J double prime is the lowest value. Okay, now this line is coming from some transition, right? So this, for this first one, this 2B bar J double prime plus 1 is the spectral line, which is 98.036. Okay, so each line is coming from some transition from J double prime to J double prime plus 1. Okay, so in that case this transition line will be equal to 2B and J double prime plus 1, or in this case it will be equal to 98.036, and we know 2B bar value. Then in solving this will give us J double prime plus 1 is equal to 98.036 divided by 2B bar, and 2B bar is 32.678 in this case, so it will be 32.678, or it will be equal to 3. So this is the value for J double prime plus 1. So J double prime value will be J double prime value will be 3 minus 1, 2. That means there is a transition from 2 to 3, from which this line 98.036 is coming. Okay, this will give me transition from 2 to 3. Okay, now check for the other line. So similarly, this 2B bar J double prime plus 1 will be equal to 130. 130.714, or J double prime plus 1 will be equal to 137.14 divided by 2B bar, or this will be equal to 130 over 714 by 32.678. So if you solve this, it will be giving you value approximately 4. Okay, then J double prime will be 3, right? So for this line 130.714, there will be a transition from 3 to 4th state. Okay, so this line is coming from this transition 3 to 4th state transition. Okay, so the previous transition was coming from 2 to 3, and this one is coming from 3 to 4. So what was given in the question? There were two adjacent lines, one at 98 and another one at 130. So from that we can calculate the line separation between these two adjacent lines, that is 2 V bar, which we are getting to be 32.678. Okay. Now, okay, bond length we didn't calculate till now. So first we calculated the rotational quantum number from which these two lines are coming. So we calculated the energy difference from this transition, which will be equal to this 2 V bar times J double prime plus 1. Now we equated this form to each line, and from that we calculated the value of corresponding angular momentum quantum number. So we got this line 98.036 is coming from the transition 2 to 3, and the line 130.714 is coming from the transition 3 to 4. Okay. Now, what we have to calculate? We have to calculate the equilibrium bond length. Okay. The equilibrium bond length of this NH molecule. We need to calculate. Okay, this we need to calculate the equilibrium bond length. Okay. So what is given? V bar is given. Okay. Now we know the relation B equal to H over 8 pi square IE. Okay. Now we can write this as IE equal to H over 8 pi square B. But here in this question, B is given in terms of wave number, right? So we need to convert this in terms of wave number. So what we have to do? We have to multiply 1C in the denominator, and this B will be converted into V bar. So from this, what we will get? We will get the moment of inertia, right? And again we know the moment of inertia formula, IE equal to mu times R naught square, where this mu is the reduced mass of this. This is reduced mass of the molecule NH. Okay. So, and this is the bond length. So from this two equation, if we equate these two equations, we will get mu R naught square is equal to H over 8 pi square C V bar, or R naught square is equal to H over 8 pi square C V bar mu. Okay. naught will be equal to h over y square c e bar mu root over. Okay, now the other value is known only except this mu value. So what is the molecule? This is NH 14N1H. So I can calculate the reduced mass for this molecule. 14 times 1 divided by 15. This will be in terms of atomic mass unit. I have to convert it to kg. Okay. The factor for converting will be okay. Okay, so this factor is 1.67 times 10 to the power minus 27 kg per AMU. Per AMU will be cancelled from this. So this will give us the reduced mass P 1.56 times 10 to the power minus 27 kg. Okay, so we got the reduced mass. B bar value we have. RH is Planck's constant, so we know all the values. So if we put all the values, we'll get 6 times 10 to the power minus 34 8 pi square C B bar is okay. We calculated 2B bar. Okay, let's convert it to 2B bar. So 4 pi square then 2B bar times mu is this value. So this was 32. $32.678. This was centimeter inverse. So we have to convert C C also into centimeter. So this will be 3 into 10 to the power 10 centimeter per second. So if we put all this value, what we'll have? We'll have 6.26. This will give us 0.0137 times under root to the power minus 34. uh, 0.0127. So this will give us 10 to the minus 18 minus 16. So it will give us 10 to the minus 8. Or this will be 1.27 times 10 to the power minus 10. So this was in terms of centimeter. Okay. Now if I convert it to meter, so this R naught will be equal to 1.27 times 10 to the power minus 12 meter, or 1.27 picometer. Okay. So P bar was given. So from that we can calculate the moment of inertia, right? Then we also know the other form of moment of inertia as this mu r naught square. Then after equating, we got the value of r naught in terms of these other parameters, and we calculated the reduced mass for this molecule NH in terms of kg. Then after substitution, we got the bond length to be 1.27 picometer. Okay, so this was the last question. So I think all of you are getting ready now. What we did today, we revised all the important questions we did last 8 weeks. Okay, so all the best for your exams, and bye bye.